So this question is, what's the impact of class imbalance to the deep learning? Okay, so class imbalancedness means, among the classes that we have to classify, so the ratio of the training data item are quite different across different classes, and so so that way, if we observe that we have much more training data items for this particular class than the other classes, and then such an effect will be reflected typically into the bias value. Any other questions? So yeah, so usually this prior knowledge, I mean, if you study the Bayesian statistics or Bayes rule or something like that, like prior likelihood and posterior, have you heard about it? Prior likelihood and posterior. And usually this prior thing, I mean the prior probability is determined or predefined in advance, right? So for example, our parameter will follow the Gaussian distribution that has a zero mean and the univariance, but actually our optimal parameter determined by the maximum likelihood estimator is actually maybe 5. For example, so it may make sense only if you are familiar with this maximum likelihood estimation or things like that. So something like this. So suppose we observed some statistics of observations like a person's height as maybe 170, 165, 175, maybe 180, and then in this case we can easily compute the sample mean of them, right? And then the sample mean will be right, so 172.5, right? So this is typically called the sample mean, right? And also if you study this kind of maximum likelihood estimation, and then you can derive that sample mean is actually the optimal estimator for our parameter, which is the true mean of our underlying distribution of that person's height, right? But when incorporating the prior in the context of Bayesian statistics, and then we impose some prior knowledge or prior belief or our kind of prejudice that, okay, the person's height, given no data at all, so before actually observing these data, we have our prior belief that, okay, so person's height will have the true mean value as 170, okay, and also the standard deviation of 5 centimeter, okay, and also we also have the prior knowledge or prior belief that, okay, this person's height will follow the Gaussian distribution. Okay, so in that case, the Gaussian distribution will only require or need those two parameters of mean and the standard deviation, right? So that way we have our own prior belief, right? And then this prior belief and also purely driven by our data, it is saying that our optimal mean value should be 172.5, right? So usually this guy and this guy is actually weighted averaged as the posterior estimation or Bayesian estimation. Okay, so in this case, this is our prior knowledge. I mean, yeah, if it doesn't make sense, and then it should be okay. But here the point is that in this case, this kind of belief or information is predefined in advance before looking at our data, right? But this, those data can also be determined, or this prior belief can also be determined by looking at just the data in a simpler manner. Okay, so in this case, what is our prior belief, or the prior knowledge related to that bias? It is related to the belief that we have much more probability of observing this dog class than the sheep class, right? So that is our prior knowledge, and that ratio is 5. Okay, so that where did this prior knowledge come from? That was also from our data, right? So such an information of having 5 times more probability for the dog than the cat, dog than the sheep, that was coming also from those simple distribution of our training data, right? So in that case, our prior knowledge is also determined by our data by taking a simple approach, right? But the actual way of determining this bias value of B1 and B2 is based on the backpropagation, right, through the gradient descent, right? So those two values are not just simply determined as those two values having this exact same ratio, right? So we have our own way to determine the optimal parameter value of B1 and B2, right? So that way, you can view this kind of our main kind of way of determining B1 and B2 as some kind of a likelihood value, but also we have this kind of prior knowledge, but this prior knowledge is also determined by our data, okay, in a simpler manner. Okay. So simply answering this question, prior knowledge, I mean, I have to explain this question. The question is whether the prior knowledge is also data dependent. The answer is yes, right? But it's not always the case. We can impose the prior knowledge as the fixed knowledge. So any questions? Okay, then K divergence is it a metric or not? If you watch the lecture video, it is not, right? So K divergence is not a metric, and which requirement does it not satisfy? Symmetry, symmetry. So right, because this why is it not equal? Simply because the definition is using P and Q in a different manner, right? So this was our definition of this K divergence, right? And so if P and Q are switched, and then this definition will become different, and so it is not symmetric. And also, although I haven't proved it, but this K divergence does not satisfy the triangle inequality. Okay. So what is the triangle inequality? We introduce or we consider third distribution as R, for example, okay, and then this KL divergence should be yep, something like this, right? So so this is not always true in the case of KL divergence, and so yeah, that way it is not a metric. Any questions? Okay. And yeah, let me address this first question. So the question is about stacking linear layers, and then why is it equivalent to just using a single layer? Okay. Okay, so so let's consider this two layers which are composed of just linear layers with no nonlinear layers in the middle. And so in this case, I'm gonna just assign some particular parameter value. So in this case, what is our function? Yeah, C is f of y. Okay, let's say it's g of y. So this layer is called g, and this layer is called f, and then it is like g dot f. Okay, and in this case g of f of 1x. I'm just writing just a simple composite function. Okay, so in this case, so what is fx? So y equals fx, because this f output of this layer called f is y, right? And so 2x plus 3, and z is f of y, and it is 4y plus 5, right? And so this c is 4y plus 5 and 4, and if we just plug this in, then 8x plus 17, right? So it's now represented as a one single layer. I mean one single linear layer, right? So stacking these two linear layers, has no meaning. I mean, it doesn't have any effect. In that case, you can just use, you can replace these two linear layers into one. Okay, but this is not always true. This is not always true. Okay, and actually, we sometimes use some famous methods in the context of natural language processing, which is called the word embedding, like word2vec or glove. You may want to use it at your project. So if you are interested in this natural language processing and this kind of domains, word2vec or glove. It's small l. But anyways, those two are two different representative methods for word embedding. Okay, so you will have a chance to study that, because I'll ask you to study that in more detail. But anyways, this word2vec is a method that uses just two linear layers. Okay, and as I mentioned in this particular example, it doesn't make sense, at least in this case, right? But when does the two cascaded linear layers has the effect or different from one linear layer? So it is like this. So suppose we start from x and 1, and then we obtained y, right? And then, so back to this example. So we have input and hidden and output layer. And what is the number of nodes in the input layer? We have just a 1, right? Because we don't usually count this bias as a input dimension, right? So we have 1 node in the input, hidden and output node, right? But what if we have a different number of nodes? Okay, so in this case, let me just add another node in the output layer. Okay, and then let's suppose we just cascaded 2 linear layers, and then it's 2 and 3. Okay, and then so we have 1 here, and then the fully connected layer is defining like this, right? So Z1 has its own function of G1 of Y, right? And Z2 has its own function of G2. Okay, so in this case, let me just assign some number 4, 5, and 6, and 7. Okay, so in this case, C1 is 4y plus 5 and 6y plus 7, right? And so what was y? Y is 2x plus 3, right? And then let me just rewrite it. It's just the same thing as this guy, right? And also, what about this? And then it's like this, right? Okay, so in this case, it is still the same as, let's see. Okay, so I have to modify this example in a slightly more complicated one, but the point that I'm trying to make is as follows. So we have a Z1 and Z2 as its own linear representation or linear combination, right? And then we want to be able to represent each of Z1 and Z2 as a linear combination of X, right? And then in that case, let's just consider single layer case, C1 and Z2, right? And then in this case, it's X, and here we will have 1, right? And then we have a freedom of assigning any linear combinations to make Z1 and Z2, right? But in this case, is it always possible to have just one node in the middle? Okay. So in this case, it is actually possible in this particular case, but if we just add another layer of x1 and x2, okay, x1 and x2, and then suppose this guy was 2 and maybe 3 and 4, right? And then this y will always have like x1 times 2 plus 3 times x1 and 4, right? And then it is multiplied with 4 and plus 5, right? So that will be this z1, right? So in this case, let's look at the ratio between x1 and x2. So in this case, it's a little bit messy, but this is C1, and C2 is 6 times 2x1, oops, 3x2, 4 plus 7, right? So it's just a slightly more complicated case where I added another input node, right? So in this case, so it's a 8x1 and 12x2, right? So in this case, 12x1 and 18x2, right? And yeah, some value, right? And in this case, for our Z1 and Z2, the ratio between x1 and x2 and their coefficient will always have the fixed ratio that was determined at the first layer, right? This guy, 2 and 3, right? So in this case, if we just cascaded these 2 linear layers, and then it will no longer be able to represent Z1 and Z2 as just an independent linear combination representation of an x1 and x2. So in other words, Z1 should always have x1 and x2 as the ratio of 2 to 3, and also Z2 will also have the same ratio, right? So yeah, you cannot break those ratio between x1 and x2 because that ratio was determined in the first layer, right? So in this case, actually, even though we have a 2 linear layers, I mean, which one is more powerful one? Like x1, x2, and 1. So this will be, yeah, one linear layer representation of having the same input and output, right? 2 input of an x1 and x2, and 2 output of an y1 and y2, right? So this is just one layer version, one linear layer version, and this one is 2 linear layer version, I mean the cascaded one. So which one is a more powerful model? So following this storyline, I think in this case of having 2 linear layers where we have only one single node in the intermediate layer, that would be more restricted model, right? So you cannot really have those different ratios between x1 and x2 for Z1 and Z2, right? So does it make sense? So it's much more constrained model. 이해가요? 이해 안 가는 사람? 다 가요? 다 가죠? Okay, so so that way, this kind of approach is called sometimes called the bottleneck structure. Okay, bottleneck structure, because we have more number of an input and more number of an output node compared to the number of nodes in the intermediate layer. Okay, so it's like if we generalize this form, and then we have really long vector as an input and long vector as an output, and like this. So in this case, even if we cascade 2 linear layers, then it will be much restricted representation when having just a single linear layers. Okay, and also we can also understand or observe their number of parameters. Okay, suppose we have a 10 nodes and maybe 3 nodes in the middle, and then what will be the number of parameters that is required to construct this neural net? So what will be the number here? So we always have to consider additional bias node, right, through our bias trick. And so in this linear transformation matrix, we'll have 3 times 11, right? So 33 number of parameters, and also similarly, it's additional bias node, and so 4 times 10, so 40. So in total, 73 nodes, right? Okay, and then let's just consider one linear case of having 10 and 10 input and output nodes. And in this case, we have a bias over here, or yeah, this additional kind of dummy node. And then our parameter, number of parameters will be 110, right? Which is larger than 73, right? So even though this guy is just a single layer, and this guy is the 2-layer neural net, I mean more number of layers, but the number of parameters may actually be smaller than the single layer one, right? So that way we can kind of intuitively understand that model on the right is more powerful, or more can represent more flexible characteristics than the left one. And also, if you're familiar with the linear algebra, and then this guy is related to the low-rank matrix factorization. Okay. Yeah, but I'll skip that part, and I think you will have a chance to look at this matrix factorization in more detail when studying the word embeddings. Any questions? Okay, then once we add this nonlinear layer in the middle, such as what is this called? Max of our output and 0. So that is called the ReLU. So ReLU is the function like this. Okay. So if we have, this y node had maybe a value of 4, and then this nonlinear layer called the ReLU will just give the same value if it is positive value, and then if it was negative value, and then it will change it into 0. Okay. Okay, so I believe I addressed this question on top. Any questions? Okay, then. So K divergence is not the same as cross entropy, right? So I already explained it in the lecture video. I recorded in some other countries. Yeah, it was a little difficult because the internet was quite slow, and also carrier divergence is not a metric, and softmax loss is the same as the cross entropy loss. I mean, they are the same thing. Do you want me to explain a little bit more details? If you want, please raise hand. Okay, and then entropy is 2 to the power of perplexity. It is actually the opposite one. Perplexity is 2 to the power of entropy, right? So, and I think I gave the some intuitions about how we understand the perplexity. But perplexity is what is the meaning of perplex? Perplex. perplex. 한글로 뭐죠? perplex가? 약간 GR이라고 토플에도 나오나 그런 perplex 동의어 한 10개쯤 외우는데. 네, perplex는 뭔가 당황하게 하다 뭐 이런 거요. 동의어 하나만 해보죠. 동의어 뭐 있죠? 네? embarrass. embarrass. 많아요. 네. Okay, so yeah. Yeah, so the perplexity is the degree of being perplexed. Okay, so it's about the confidence or uncertainty of the outcome. Okay, so suppose you played some poker with your friend, and then yeah, suppose you are quite certain that what the opponent has has in terms of its a particular card value, face value, or something like that. Okay, so yeah, so 이거 어렵네. 도박을 영어로 하려니. Okay, but so perplexity is something like this. So suppose you have we roll the dice, and then that dice has always producing the fixed value of maybe 2, okay? Even though it has 6 different values, but from your empirical experiences, and then you always observed that this dice is producing the fixed value of 2, okay? So in this case, what would be the perplexity? I mean, the degree of being perplexed by watching the unexpected values. So in this case, there is no perplexity, right? Or there is no uncertainty, right? Okay. And then what about this case of our dice? Yeah, even though it has 6 different values, but our empirical experiences says that our dice is producing equally either 2 or 3. So in this case, we can expect our outcome to be just between 2 of these values, right? So in this case, we will be kind of perplexed, I mean twice kind of more than the first case of expecting just a single value, right? Okay, so the number of possible cases that we can expect can be just understood as a perplexity. So in this case, the perplexity will be 2, and what about this case? It is if we are certain that we will observe this outcome will be just a fixed value of 2, and then it will have the perplexity of 1. So you can roughly or intuitively think of it as the number of possible outcomes that you can expect. Okay. Okay. So in this case, I mentioned that we have there is 0 uncertainty, right? We are 100% certain or sure that our outcome will always be this 2, right? And so in this case, what will be the entropy or uncertainty? In this case, entropy will be 0, right? Entropy will be 0. And that entropy, 2 to the power of the entropy is actually the perplexity, right? So it means that, the possible outcome that we can expect will be just only 1, okay? So that is the same situation that, we have 0 uncertainty. Okay, so this perplexity is quite often used for the evaluation measure, okay? So suppose we perform the 10 different classes and multi-class classification among 8 different classes. Okay, so in this case, what will be the random guess and their perplexity? I mean, what will be the perplexity corresponding to the just pure random guess? I mean, random guess will be just picking up one among the 8 different values equally. So in this case, perplexity will be just an 8. Okay, but somehow you trained your classifier very well, Okay, and then given the input feature value, okay, input feature vector, you are always like, yeah, you are 100% certain that given this particular input feature vector, I mean the correct classifier is this particular one. Okay, so in that case, given our input feature vector or input information, the situation is something like this. Even though we have 66 different face values of our dice, but in this particular situation, we expect, I mean, we are certain that outcome will be 2, right, with the 100%. Okay, so in that case, from the classification perspective, our classification accuracy is 100%. Okay, so in this case, what will be the perplexity? Perplexity will be 1. Okay, so if you read some papers and then see the perplexity being 1, and it means like perfect classification. But what about the perplexity being 2 or maybe 1.5? Okay, in the mid, which is somewhere in the middle between 1 and 2. So in the case of 2, and in that case, given the input feature vector, and then your classifier is actually equivalent to random guess between only 2 of them, only 2 of the possible classes. Okay, so that is the intuitive understanding about the accuracy measure of your trained classifier. Okay. Any questions so far? Okay, the answer for this question is logit. Okay, so this was covered, right, in the class, I mean the lecture video, and also in the CS231 and original video lectures. So so this is our softmax loss, right? And then if we just perform the random guessing on this case, and then picking up randomly among the 4 different classes, and then I mean the picking up the ground truth class will be just 0.05, right? So that way it's like this, and so the loss is 2. And then what will be the perplexity? So this is the perplexity is 2 to the power of 2, so the perplexity will be 4. Okay, so as I mentioned, if the perplexity is 4, and then our classifier is like doing the equally picking up among 4 different classes. Okay, so that way the perplexity is related to this cross entropy or K divergence and things like that. Okay. Any questions? 네.
퍼플렉시티가 가능한 아웃컴스 농구라고 하셨는데, 그럼 그때는 모든 경우의 수가 같은 확률일 때, 균일한 확률을 가질 때만 그걸
네.
넘버가 나오는 건가요?
네, 그게 약간 내가 그 스페셜 케이스로서 이야기를 좀 이해를 돕느라고 한 거고요. 네. So so this is our original softmax loss, right? And then it doesn't matter how many classes we have originally. So suppose our problem is the multi-class classification among 1,000 different classes, or maybe 10 different classes, or maybe just 5. Okay. So regardless of the total number of classes, at the end, after training our classifier, and then our average loss of this softmax loss was like pi was 0.5. Okay, so that is the average loss. So what does that mean? So this pi is what? Yeah, so more exactly, it's like this pyi, right? The predicted probability corresponding to the ground truth one, right? So if given the particular image and then its ground truth was cat, and then what is the predicted probability that our classifier assigned to the cat class, right? So on average, suppose that probability was 0.5, okay? And then this loss value of negative log 0.5 is possible for each of all the classes, right? So even though we have 1,000 classifier, our loss function, loss value is ending up with this guy, or if we had 10 different classes, our loss may have the same value and 5 classes, and also the loss may be having this value, right? So in this case, yeah, roughly, it will be much more difficult to achieve this level of softmax loss given much more number of classes, right? But anyways, if you ended up having this loss value of negative log 0.5, and then it means that your classifier is roughly predicting like picking up one among the two, and among the two, the ground truth answer exists. Okay, so that's the meaning of it. Okay, so your classifier has assigned the probability of 50% to the ground truth probability, and then it doesn't matter how many other or negative classes you have. So in this case, the negative class would have 999 and 9 and 4, right? But it doesn't matter. All the negative classes and the total amount of probability that your classifier assigned was the rest of the probability of 0.5, right? So it means like this situation is equivalent to picking up like the ground truth values among the two equally possible cases. So does it make sense? So in this case, the perplexity will be 2. And if this value was 0.25, and then what is the probability? The total probability that the classifier assigned to the all the negative classes, it will be 75%, right? So in this case, it doesn't matter how many negative classes we have, but the total number of probability that our classifier have assigned to the negative class is 75%. So that's the important part, or that's the all the information that we need to evaluate our classifier's performance, right? And that's how this perplexity measure is computed, or the softmax probability, the softmax loss is computed. Okay. So yeah, in this case, it's like picking up ground truth among the four different classes. Any questions? 혹시 좀 뭐 이해 안 가면 내가 저기 한글로 다시 설명을 해줄 테니까 이야기를 하세요. 오케이. Oh. Yeah. So yeah, it's called the wisdom of crowd. So majority of students gave the wrong answer, and then it means I might be wrong, right? Actually, what I did was I recognized that the answer was lying in the middle too much, so, like between B or C. So I wanted to have one question has an answer at the extreme value of A or D or E. Anyways, so the correct answer is A. I can almost, there is a case that one-dimensional layer function can be powerful than. Yeah, I don't understand this question in the middle. Can anyone elaborate it or explain a little bit more? Okay, maybe then, maybe the student can take, can discuss offline or after the class with me. Also, two models are not independent from. When you say independence, I want to know what kind of aspect you intend to. I think both of two models are not independent from the coefficient of an x. When you say independence, I want to know what kind of, So it seems to be related to kind of this question, right? So in this particular case, if we have a bottleneck layer that has a much smaller number of nodes in the intermediate layers, and then we can always we are restricted to have the fixed ratio fixed ratio parameters assigned to x1 and x2, right? So if we just so in this case that fixed ratio is like 2 to 3, right? But in this case we can just freely set up or assign any different parameters of 2 and 3 and maybe 5 and 1. So certainly Z1 has the different ratio between x1 and x2 as 2 to 3, and Z2 has the ratio of 5 and 1, right? So we basically have a freedom here to choose whatever ratio that we want to obtain each of Z1 and Z2, right? So that's that way this one layer is more powerful, right? Okay. So I hope you guys studied carefully this backprop lecture on the backprop. Okay, so this is really the key concept to train whatever complicated neural nets. Okay, so whether it's just a standard fully connected layers or convolutional neural layers, neural networks or recurrent neural networks or any other types of neural nets, and sometimes this backpropagation doesn't work. In the case of having some special layers of having some kind of discrete kind of outputs. So in order to understand why a particular layer is not, it's not working with the through the backpropagation. You have to have a deep understanding of this backprop. Okay. Let's see. So I want to give a little bit more intuitive understanding by using a simpler kind of example. Let's just consider this linear regression of having a one-dimensional input of an x, and then our model is ax plus b, and then let's just draw our computational graph. So in this case, so this is one way, like this, and then here we have an A and B, placed at the edge. But when thinking of the backprop, so this is not a good way. Okay, this is not a good way. So all the variables and the parameters, I mean, whether they are parameters or the variables. So in this particular case, A and B are parameters that we have to find the optimal parameters, right? Optimal values. And then also X is our input variable, right? But from the perspective of a backpropagation, they are all the same, right? So we shouldn't, backprop doesn't differentiate them in principle, right? So you will see why. And so in this case, I can draw this computational graph as this guy, A. So it is multiplied together, and we have another node B, and then they are added together. So this is Y, right? Okay, then suppose we have just one single training data of X being 1 and Y being 4. And then the current parameter values are 2 and 1 for A and B respectively. So in this case, so we typically set up, so I think you have understood some examples shown in the lecture. So X is maybe 1 and 2 and 2 and 1 and 3, something like that, right? And then we set up the gradient value as 1 at the final output node, right? And where does this gradient value of, initial gradient value of 1 come from? So we have to actually compute our, we have to complete our computational graph from the loss function. What is our loss function to minimize? So why do we compute the gradient? It is because we want to minimize some objective function that we want to minimize, right? And so we have to represent our objective function as a computational graph. And so what is our objective function? From using least square or L2 loss, in the linear regression case, our loss function will be this, right? So we have just one single data items. So it's like this, right? And then also, if we have another examples like 2 and maybe 5, and then our loss function can be represented as this, right? Okay, but let's just consider the simple case of having just a single data item, and then let's suppose so this is the predicted value, right? And then this guy is our ground truth value, and then this guy is Y and minus, right? So that is up to this point, and then the input value to the input value squared is our loss function, right? So now we completed, or we finished our computational graph to represent this loss function, right? So that way we want to minimize that loss function, right? So starting from here, so from here we apply the chain rule over here as this. So what is the chain rule? First of all, we just think of that function, entire function itself, as the single variable x, right? Single variable x, and our loss function is just this, right? And so in this case, so this is our x. I mean, currently like temporary like capital X, and in this case, what will be the partial derivative or the gradient value with respect to capital X at this point? It will be just 1, right? Because whatever function that we have, and then if we just treat it as just a big X, and then if we compute the gradient, and then it will always produce 1, because y equals x, and then its gradient will always produce 1, right? So our 1, or the gradient value, will start from here as 1. Okay. So in this case, 1. And then y2 is 5, and then it's -2, and then it's 4, right? Okay. So far so good. And then now we have to compute the gradient at this point, right? At this point. And then it is like, so how does chain rule work? We obtain the gradient as 1, and then we now get inside of this original capital X, and then we now set this guy as x, okay? And then in this case, this value will be our temporary capital X, and then x squared, right, will be our L, right? And then in this case, we just have that value and multiply with 2x, right? 2x. And then what is this 2x? So x was initially -2, and then it's -4, right? And then -4 is actually multiplied with, so the gradient at this point will be -4 times 1, and so like this, right? And then this value, we have to backpropagate this node, and then this node, we now have this this guy, and this guy is actually like x minus y is this node, right? And so if we compute the partial derivative with respect to x, and then it will be 1, right? And so 1 is multiplied with this value, right? And then what about this guy? Partial derivative with respect to y, it will be -1. And so this -4 would, -4 would be multiplied with 4, right? Right? Okay, and then now this -4, in the case of add gate, and then it's x plus y. Here we have an x and y as a temporary capital variable, and in this case, the partial gradient derivative will be always 1. So that way, this gradient will be just duplicated as the same values, right? And then in the case of this multiplier, the gradients are switched, right? Switched. So it's like -8, and then it's -4, because this guy. Okay. So this is kind of a mechanical process that we will follow after we complete this computational graph that represents fully our loss function, and then we just backpropagate through this computational graph, right? Okay, so here, this mechanical process, you can just train yourself by following these mechanical process. But what I wanted to emphasize here in this case is that through this backpropagation or completing this computational graph in terms of the forward propagation values and also backpropagation gradient values, it doesn't differentiate whether a particular variable is parameters or input values or intermediate outputs. Okay. So what does that mean? What does that mean? So usually we just use the parameters that we want to update through our gradient descent is those two values of an a and b, right? So if a was 2, and then let's use the step size of 0.1 and then times -4, and then 2.4 will be our updated parameter value a, and in the case of b was 1. It has the same gradient value. Okay, so this will be just a result of one step of gradient descent update, right? So in this case, let me point out this thing. Can we just update x value as well, right? So let's suppose we update x by using the gradient descent as 1.8, right? So ideally we have no problem in doing so, right? So the theory of this backpropagation doesn't prevent you from updating this x value, okay? And then why do we not just update this x value? It is because it just doesn't make sense, okay? It doesn't make sense, okay? So what's the meaning of updating the input value x, okay? So it's like this. So you have a particular height and weight, for example, like 80 kilograms and also 160 centimeter, which is who is certainly like overweighted. And then this guy has the diabetes as a particular disease. Okay, so in this case, your current model is saying this guy is only having the probability, is only 80% of having the probability of having the diabetes. Okay, so in this case, the ground truth value is 1, and our prediction value is only 80% of being, of having diabetes, right? So in that case, we would want to minimize the loss value in order to make it small in terms of the difference between the ground truth value of 1 and the current prediction value of 0.8, right? So in this case, the meaning of updating a and b in this manner, is that we want to just minimize the difference or make the difference smaller or minimize our loss function, right? And then what's the meaning of updating x value? So x will be our feature value, so it will be considered as maybe either height or weight. So I'm currently 100 kilogram and 160 centimeter, but in order to minimize or make the difference between the ground truth value and the predicted value smaller, and then this x value can be updated as this value, and then it means that if we update x in that manner, and then that is just another way of decreasing the loss function value. Okay, but suppose yeah, that kind of updating is saying that, okay, so I'm currently 100 kilogram and 160 centimeter, but in order to decrease the loss function value, and then my weight of 100 kilometer should be larger as 110 kilogram. Okay, so if I increase my weight, and then the current loss value can be smaller. Okay, can become smaller. Okay, so that is certainly, yeah, one legit way of decreasing the loss value, right? But as I mentioned, that doesn't make sense because we cannot just freely change the input feature values, right? So given a particular person's height and weight, yeah, we cannot freely change them, right? So that way, in practice, it doesn't make sense to update these input feature values. Okay, so that's why we don't just apply gradient descent on the input feature value of an x, right? Even though we have no problem of obtaining gradient values, whether they are just the parameters or the yeah, input feature values. Okay, but yeah, so you will see, yeah. So interestingly, sometimes we are actually updating that input feature value, sometimes depending on the task settings. So one representative example is this guy, style transfer. So I think you have seen this kind of example of giving this a realistic photo and another artistic images, and then you kind of impose that style from the artistic images into the given realistic photos, and that way we obtain this output, right? So in this case, what will be our input feature values or input values? Because we want to change, yeah, because we are giving this image as an input to our model, our machine learning model, typically, yeah, implemented as a deep neural networks, and then height, I mean the input values corresponding to height and weight are the pixel values in this particular case, right? So we want to, yeah, optimize or change the input values in this particular task setting. So in this case, it makes sense to change the input values, right, for this particular problem called the style transfer. Okay. So yeah, later you will see, we will study this example in more detail. But anyways, yeah, I wanted to focus. I wanted to emphasize that whether they are parameters or input values, yeah, you have no problem of applying gradient descent. Okay, and also there is another type of node in this simple example. So input values and parameters of an A and B, right? And also we have all these intermediate nodes, okay, which are typically corresponding to the nodes in the hidden layers, okay. So those nodes, I mean those internal or intermediate nodes, will also have these gradient values, right? Okay, and then can we just apply the gradient descent on these intermediate nodes? For example, like given this value, so something like this, 2.4, right? So we have, yeah, in principle, we have no problem of updating that intermediate values through the gradient descent, right? So that way we can directly, like, optimize or update the intermediate values. But in this particular case, it doesn't make sense either. Okay, why does it not make sense? Because, yeah, because this intermediate node is not an independent variable, right? It is actually like output from another, I mean other independent variables. So in this case, x and a are kind of independent, yeah, can be viewed as an independent variable that we can kind of change their values, right? But those intermediate node is actually the output from those independent nodes, right? So that way it doesn't make it doesn't make sense to directly update this intermediate node. Okay, but still, yeah, that kind of thing of directly updating intermediate node is also possible, and some advanced method is actually using it. Okay. Yeah. So yeah, although there is no representative case that I can describe easily, but yeah, in principle, you have, yeah, I want you to understand, in principle, that is also possible. Okay, and yeah, if needed, you can utilize that kind of idea. Okay, in that case, it's like intercepting some intermediate values into some other values that can directly optimize or minimize the loss functions. Okay. Anyways, okay, and then and I want to discuss a little details about why chain rule works. Why chain rule works. Okay, so for example, like this. So it is actually a composite function. Composite function means x is first going through this sine function, and then this output, intermediate output, is also going through the squared function, right? So that is the simple computational graph of this guy. Okay. Okay, and then in this case, let's see, it is c and z, and y is sine x. So this is y and z. Okay. So we want to obtain the partial derivative with respect to x, and then it can be written simply as this form, right? And also it's like it is actually even be written as this guy, right? So suppose this guy is the function that we want to minimize, okay? Mean of z, or we want to minimize sine x squared, okay? So in this case, currently x is maybe 30 degree or something, okay? Or (30도가) 몇 파이죠? Okay. Okay. Okay, so in this case, we want to obtain the partial derivative or gradient with respect to x, right? So in this case, it is like this. So we start from here, gradient of this. So it's like pi over 6, and then it is 1 over 2, and it is 1 over 4. So that is a forward pass, right? And then the backward pass will be 1. And what is this guy? So it's like, so we just look at this sine x as capital X temporarily, and x squared, and 2x, and then x is this value, and then this value is 1, right? And then it is actually 1 times 1. So it is 1, and this is also 1, right? And then what about this guy? So when x is pi over 6, and then it is having this, I mean this is a derivative. So right, so this is the backprop result, right? Okay, so why should we multiply all these values? Why should we multiply all these values? Why should we multiply this? So it is, yeah, so yeah, let me just explain it in maybe 2 minutes. So how this chain rule works, or the intuitive understanding about this chain rule is as follows. So we want to have, we want to obtain how much changes z has with respect to the changes of an x, right? So it's like this. So if we have this kind of function, and then what would be the derivative at this point? It would be the slope of this. And then what's the meaning of it? The meaning of it is, so if we just move like with the 1 centimeter larger, and then how much y value changes, right? So that ratio is the slope, and that is the definition of the gradient, or the first order derivative, right? And then what about the chain rule? Okay, so so this is like x to y and y to z. So we want to obtain how much z changes with respect to the changes of an x, okay, when they change with the 1 centimeter. So this is an x. So this is an x, right? And then suppose when x changed with the 1 centimeter, and then y changed with the like square root 3 over 2, right? So that is the changes, the amount of change of y, okay? And then when this amount of change occurred for y, okay, so it's like x and y and z, and so this corresponding y value was 3, and then we go to the value of 3 at y, and then here we consider this slope at this point, right? So this is still, I mean, dz over dy is actually the amount of changes of z when y changes just 1 centimeter, right? So that's the meaning of this guy, or the slope of the graph between z and y, right? But y does not change only 1 centimeter, because that is just a dependent or intermediate variable obtained by x. So when x changes with the 1 centimeter, and then y change it with this amount, and then we have to replace this value as like square root 3 over 2, right? So that way we have to multiply this changes when y changes the 1 centimeter by the amount of this value, okay? So that's the meaning of just keep multiplying those slope values. And then what is this guy? The first one is always like this graph. So z equals z. So in this case, whatever positions, the slope will always be 1. So it will be just 1. Okay. Not sure if it's it helped your understanding about why this chain rule should be true, but yeah. Okay, so that's it for today. And then until Wednesday, I will assign you guys to for some other additional video lectures to watch, and then that will be also the scope of the quiz next class. Okay, thank you. 네.
아까 그 서프맥스 로스 계산할 때 랜덤 이니셜라이제이션 하는 거 있잖아요. 결론 자체는 클래스 영향 개수에 별로 영향이 없는 거 아닌가요? 클래스 개수가 1000개든 100개든 10개든
네.
이게 결국은 어떤 특정한 그
네.
확률 값을 브라운 트루스랑 같은 확률 값으로 가는 거잖아요. 그게 그 클래시파이어가 얼마나 잘 클래시파이를 하는 건지를 나타내는 지표인데, 그러면은 클래스 개수가 1000개든 100개든 10개든 그럼 상관없이 그냥 클래시파이어가 얼마나 잘.
그러니까 클래스 개수가 만약에 다섯 개면
네네.
노드가 이렇게 아웃풋 노드가 5개로 빠질 거고요.
네, 그죠.
랜덤 이니셜라이제이션을 하면 얘네들 5개 노드가 이제 그냥
확률이 일정하다라고 보는
맞아요.
거죠.
네.
아, 그래서 그러면은
네.
브라운 트루스의 걸릴 확률이 5분의 1이다라고
그렇죠.
판단해서
그렇죠. 그럼
플렉시티
하나의
계산을.
랜덤 개수를 하면 20%만 얘한테 걸릴 거고요. 그러면은 이제 얘에 대해서의 그 로스, 그 소프트맥스 로스는 마이너스 로그 20%가 되는 거죠.
아, 네. 아, 그리고 아까 그 뭐지? 시험 보는 거 있잖아요.
네.
시험 보는 거 제가 그 핸드폰 로그 뒤로 가다가 또 눌렀는데 제출이 아마 2번 됐을 것 같은데.
아, 네. 그럼 그거는 아마 그거는 더 높은 점수로 해줄게. 아마 둘 중에 하나가
답은 똑같아요. 그래서
네.
그냥 똑같이.
알았어요.
네, 알겠습니다.
아까 마지막에 L2 적용할 때
네.
원래 L2 그 레귤라이즈 할 때는 웨이트 제곱을 더하는 거잖아요.
아, 네.
근데 여기는 Y가 포함돼서
이거는요.
네.
이게 아까 L2 그거는
네네.
레귤러라이저가 아니라
네네.
네, 레귤러라이저가 아니라 네, 우리가 이제 갖고 있는 그 이제 리그레션에서 로스가
예.
이 저기 프리딕션 밸류 빼기 타겟 밸류의 제곱이잖아요.
네.
이거를 그냥 쓴 거예요.
그냥 그 의미부터.
네.
네네.
여기다가 만약에
네네.
A 제곱 B 제곱의 그 로스가 들어가면,
네네.
그러니까 그 L2 레귤라이제이션이 들어가면
예.
이쪽에 이렇게 또 걸려요.
네네네.
네. 그래서 여기서는 그거는 고려는 안 합니다.
아, 네네. 그리고 아까
네.
이거 설명하실 때
네.
그 비율 유지됐다고 하셨잖아요.
네네.
그거 왜 말씀하신 거예요?
아, 그게 그러니까 중간에 노드가 적어진 상태에서 다시 이렇게 커지는 식으로 이제 리니어 레이어를 이렇게 두 개를 연속하게 쓰면,
네네.
그러면 리니어 레이어 하나만 썼을 때의 거기서 표현할 수 있는 것에 비해서 얘 표현력이 확 작아진다는 거예요.
아, 네네.
네, 왜냐하면 아까도 봤듯이 이제 그 레이어 하나로 그냥 바로 구성을 해버리면,
네네.
바로 구성을 하면 어디 있나? 어디 있을까? 네, 여기서 이게 하나로 구성을 하면
네네.
Z1, Z2에 대해서 걸리는 파라미터를 내가 독립적으로 이 X1, X2 그리고 상수항에 해당하는 걸 내가 마음대로 세팅을 Z1과 Z2를 따로따로 독립적으로 할 수가 있잖아요.
네네.
근데 여기 바틀랭 레이어가 있는 경우는 여기 첫 번째 레이어에서 2랑 3으로 이렇게
네네.
됐다.
네네. 네. 마지막 한 개만 더.
네네.
그 아까 여기서 처음에 저는 이제 처음부터 어떤 평균으로 바이어스를
네.
주어주고
네.
학습하면서
네.
계속 바뀌는데
네.
처음에 예를 들어 아까 덕이 캐퍼가 1200을 더 켰잖아요.
네.
그러면
차원?
네.
그럼 데이터 개수.
데이터가
네네.
계속 컸는데
네.
학습이 돼도
네.
나중에도 결국 그 B1이 비트보다 큰 건가요? 그러니까 크단 사실은 유지가 되는 건가요?
대부분 그래요. 네. 네.
네.
근데 꼭 그렇지는 않을 수 있어요.
아, 네.
그러니까 아까 얘기했던 거는 그러니까 그 바이어스는 그러니까 평균적으로 그러니까 바이어스를 제외한 부분, 그러니까 이쪽과 이쪽에 해당하는 평균 값이 두 개의 클래스 간의 데이터들 넣으면 이 두 개의 평균 값은 0에 혹은
네네.
같은 평균 값이 나온다라 그러면
네네.
이 바이어스가 큰 쪽에
네네.
그러니까 이제 그게 더 많이 이제 좀
아,
확률을 부여를 하게 되는 건데
네네.
아마도 대부분 그렇게 나올 거예요.
아, 네.
근데 이제 모델이 볼 때 이제 여기 단에서 값이 그냥 이거의 평균 값이 0이 아니라 더 큰 값으로 이렇게 내주도록
네.
하면
네.
그러면 이제 얘는 어떻게 보면은 네, 여기서 이미 그 평균을 올려버린 거니까 이 바이어스만 따로 뚝 띄워놓고 비교를 했을 때는 그렇지가 않죠.
네. 감사합니다.
다른 게 아니고 학부형생 분이 했었는데
네.
답은
이름이 뭐죠?
오영진.
네. 내가 행아웃으로 메시지를
안 보내셔서.
네, 맞아요. 네. 내가 오늘 중에 다시 이메일 줄게요. 네.
무슨
네.
학부형생이랑 졸업 프로젝트 관련해서
네.
이메일
이름이 뭐죠?
신희성이에요.
내가 이메일 안 줬나요?
주셨는데
네.
그
네.
어떻게 하면 되는 거죠?
그거 어떻게 할래요, 그러면?
그게
주제를 그러면
졸프를 이렇게 반드시 해야 되더라고요. 그러니까 이게 정보통신대학 소속이어서 이게 뭐 인턴이나 이런 걸로 대체가 안 되고.
네. 그러면 그 팀이 있나요? 없죠.
팀을 김태리 학생한테 약간 얘기는 해봤는데
네.
그러니까 교수님 동의가
네.
있어야지 되는 거니까.
네, 나는 괜찮아요.
그-
거기에 같이 해도.
그래서 뭐 거기도 괜찮고 아니면 아무데나 배치를 해주셔도
네.
돼요. 졸업을 해서.
그래요. 거기 테리 학생이랑 같이 해보면 좋을 것 같은데요.
예.
아니면 뭐 텍스트 쪽을 하는 저기 학생들이 좀 몇 명 있는데
예.
또 뭐 그건 이미지고 이쪽은 텍스트인데 본인이 뭘 좀 원할지.
이미지 텍스트 다 좋습니다.
네.
어떤 해주시네요.
네. 그럼 일단 뭐 테리 학생 쪽이랑 한번 이야기를 해서 그쪽으로 한번 해보면 어떨까 싶은데.
예, 알겠습니다.
그래요.
예.
네.
저 혹시 학부
네.
그러니까 그 랩 인턴이랑 학부 인턴이랑 아까 혼동해서 제가 사용을 했었는데
졸업 프로젝트 얘기하는 거죠.
졸업 프로젝트 말고
네.
그 교수님 연구실에서 약간
네.
학부생들
네.
하는 것들 있잖아요.
네.
뭐, 그걸 어떻게 할 수 없을까도.
그래요?
예.
잠깐만요. 그럼 먼저 이걸 좀 해결을 좀. 네.
저는 그냥 기초적인 질문을
네.
확인차 여쭤보려고 프로퍼게이션 자체가 그러면은 그 기존 값이랑 예측 값을 그 서로 그 계산을 해가지고 차이만큼 그 그레디언트 디센트를 이용해서 가서 최적의 웨이트를 찾는
네.
그런 과정이라고 생각해요.
네.
근데 아까 그 교수님이
네.
그 X 관련해서
네.
그 말씀하신 게 잘 이해가 안 가서
그러니까 이게 그레디언트라고 하는 값들이 이제 의미하는 게 뭔가를 생각해 보면, 여기 이제 우리가 구하게 되는 요 각각의 노드들, 그러니까 이게 파라미터든 인풋 값이든 상관없이 이제 그레디언트 값들은 다 모든 중간이든 처음이든 뭐 그게 파라미터든 인풋이든 다 나와요, 그죠? 그리고 이 그레디언트를 가지고 이렇게 그레디언트 디센트, 그러니까 빼기를 한다는 건 뭐냐면 이 값들이 요 변수에 대해서 이 주어진 이 펑션 있잖아요. 이
네.
펑션을 이렇게 올리는 그 슬로프, 그러니까 그 기울기 값이잖아요.
네.
그러니까 이 말은
근데 약간 가중치를 이만큼 바꾸면 좀 더 정확하게
네,
그렇게 생각합니다.
네.
리설트와 그냥 비슷하게
네.
할 것이다 해서 계속 이렇게
네네네.
러닝 하는 건데
네.
아까 뭐 그
네.
당뇨병 그거 얘기 말씀하셨을 때
네.
그 부분이
뿅.
네.
뿅. 그러니까 어쨌건 우리한테 주어진 무슨 펑션이 됐든지 간에 그
네.
펑션을 줄이려고 하면 그레디언트 값을 구해서 그 값을 어떤 특정한 스텝 사이즈를 곱해서 기존 값에서 이렇게 빼면 이제 줄어들게 할 수가 있잖아요.
네.
그러니까 이제 A를 이 그레디언트를 적용을 해서 업데이트를 한 이 값이나 이 값은 뭐냐 하면 이렇게 업데이트를 하면 이 펑션이 줄어든다는 뜻이고요.
네,
작아진다는
네.
뜻이고, 역시 x도 지금 x가 입력 변수여서 주어진 값이 1인데 지금 그 값에 요 그레디언트를 해갖고 요 1.8이 되면 이 x가 1에서 1.8이 됐으면 역시 이거가 또 얘가 움직였을 때 이거를 줄이게 되는 어떤 그런 변화를 만들어내는
네.
거라는 거죠. 근데 이제 x를 우리가 이렇게 업데이트를 직접 하지 않는 거는 이제 x를 우리가 바꾸는 게 말이 안 되기 때문에
네.
그렇다는 거예요.
네.
그러니까 주어진 입력 데이터는 입력 데이터지 그거 자체를 뭐 바꿀 수는 없는
네.
거니까. 네. 그래서 그 아까 그 몸무게 뭐 그런 얘기를 한 게
그러면은 이렇게 계산을 해도
네.
그 x 값에 대한 이 값은
구하지만 안 쓰는
네,
거죠.
굳이 쓰지 않고
네.
그냥 나머지 그
네.
저희가 정해준
네,
A랑 B
우리가
값을
이제 우리가 이렇게 업데이트를 하는 그 대상이 되는 그 파라미터들만 요 해당 그레디언트를 적용해서 업데이트를 한다는 거고요.
네.
근데 아까도 얘기했듯이 이제 이 백프랍을 하는 관점에서는 여기 있는 모든 노드들이 다 그레디언트들이 다 모든 노드들에서 구해지고 필요하다면 그리고 그게 말이 된다면 하여튼 중간이든 하여튼 입력 값이든 우리가 직접적으로 바꿀 수가 없는 애들인데도 걔네들을 그러니까 일반적으로는 직접적으로 바꿀 수가 없기 때문에 걔네들을 단지 업데이트를 안 하는 건데 어떤 상황에서는 걔네들을 업데이트를 할 수도 있다는 거.
네.
그래서 그 어제 레빈턴 확인해서
네, 그게 그거를 내가 담당자한테 전화를 해봤는데 안 받더라고요. 그리고 내가
그래요?
이메일을 보냈는데도 이메일 연락이 아직 없어요. 아마 그분이 오늘 휴가 중이시지 않을까 싶어요. 그래서 하루만 좀 더 기다려 볼래요. 나도 답을 못 받아갖고 내가 알려주지 못했어요.
네, 알겠습니다.
네. 아, 네.
영생
네네.
뭐죠?
아,